Hi, in this video, we're going to do a DC analysis of a common source fixed bias amplifier. We're going to figure out expressions for VGS, ID, VDS, VD, VG, and VS at the Q point, i.e. the quiescent point or the quiet point, if you like. That means when there are no signals present. Okay. So before we do that, we need to understand what we need to do in terms of DC analysis. First thing we do is we open all capacitors, because at DC values, the impedance of capacitors are infinite, right? If you guys remember, the impedance of a capacitor is 1 over j omega c, and omega is 2 pi f, and f is 0. So therefore, 1 over j omega c is infinite ohms, right? So at DC values, C1 and C2 becomes a cut, an open circuit. All right. So then what's left will just be the part in the middle. All right. So because we're removing C1, the signal source, VI, will also be absent. All right. And then we'll figure out using appropriate formulas, if you like, for the transistors' voltages and current relationships. All right. All right. So let's begin. So once we remove the C1 and C2, what we're left with is just the circuit in the middle here. Okay, so let me just do some labeling. So there is a current that flows down, right? And since it goes through RD, I'm going to call that IRD. All right, so that's the current flowing down. There's a drain current, ID. So I'm going to label it here. Let me just align that. All right, so the arrow. All right, so ID flows into the drain. All right, so because there's a current IRD going through RD, there's going to be a VRD, a voltage across RD. Okay, and then there's going to be a voltage drop across VDS. That's the from drain to source, right? So from drain to source. From drain to source, there's going to be a voltage drop. We call it VDS. There's going to be another voltage drop between gate and source. We call that VGS. And then, of course, since JFET has a barrier between gate and the conducting drain source, basically we can treat the gate current as 0, right? So there will be no gate current going into the gate. There will be no current going into the gate. All right. All right. So let's have a look at what we can do. Well, we're going to say at Q point. All right. So let's create some expressions. Okay. So what can we do? Well, we can look at VRD. All right. So we can do like VRD. So let's have a look at VRD. VRD is just Ohm's law. V equals I times R, so it's just going to be I RD times RD. So that's our first equation. Yeah, VRD equals I RD times RD. Now, what else? Well, let's have a look at ID. Well, ID is basically the drain current for a JFET. Now, drain current for a JFET, in this case a N-channel JFET, is just given by this quadratic equation. Yeah, ID is equal to IDSS, where IDSS is the saturated drain source current, times 1 minus VGS over VP, where VP is the pinch off voltage of the device. All right, so VGS is just the voltage between gate and source. All right, so we know what ID is. That's the expression ID. Now, since there is nothing, no load connected to the drain because of C2. Yeah, C2 is now an open circuit. So therefore, IRD is equal to ID, right? So that's the other expression that we can write. IRD is just simply equals to ID. Okay. All right. So what else can we write? Well, we can write about VDS. If you look at VDS, I mean, VDS, if you like, is the total voltage from top to bottom is just VDD, right? From top up here, this node, the top node, all the way to ground, that's just VDD. So via KVL, we can write an expression for VDS in terms of VRD and VDD. All right, so that's just in terms of KVL. So we're going to write VDS rather. VDS is going to be equal to VDD minus VRD, right? Okay, so since we have an expression for VRD, we can write as VDD minus IRD, RD. Oops, sorry, minus IRD, RD, okay? All right, so, and IRD is just ID, right? So we can write that as well. So this is just simply ID, all right? Okay. All right, so remember, yeah, all this is at Q point, meaning there are no signals coming in. It's just purely DC biasing. And we've pretty much, so far we've done the VDS, that's the VDS, the expression for VDS, just a VDD minus IDRD. Okay, and ID, well, ID is just simply IRD, which is simply this expression here, right? So let's have a look at VGS. Okay, so VGS is a bit interesting. So let's have a look at VGS. Well, okay, so since there are no currents flowing into the gate, right? And the only path for current to flow from this voltage source is through the wire, right? But since there's no current going there, therefore there's no current going through RG, which means since there's no current going through RG, the potential difference at the top and bottom would be the same. So therefore, VG is just negative VGG because basically the voltage drop across RG is just zero, right? There's no current flowing through here. Right, so I mean, if I want to write a full expression, I could write like this. I could write an equation for VG, for example. Oops, sorry, VG. Right. So VG is simply equals, again using KVL. Imagine a current flowing through RG. All right. Okay. So let me. So my VG is pointing up. Right. This VG is pointing down. Okay. So if I were to define a current that is flowing down. Yeah, if a current is flowing down, then the VRG will be pointing up, right? So I can write the VG is equal to VRG minus VGG, right? Or rather, I could say plus negative VGG, right? Okay. So VG, that's the voltage from gate to ground. It's just the voltage across RG plus the voltage across VG. Now, I say plus because I want to put an arrow pointing up, but then of course it is negative to negative VGG because that's how the VGG is oriented. All right, so that's VRG. Well, actually, let's just do it straight away. Well, the current going through RG is going to be zero, so it's going to be VRG is going to be zero minus VGG, right? Sorry. Okay, which is just negative VGG. So that's it. That's basically VG. So the VG that we're interested in. All right. Okay. So what else can we write? Well, we want VS, for example. Well, VS is actually connected to ground, so that's fairly straightforward. So VS is just equals to 0 volts. Okay. So we got VS, we got VG. How about VD? Well, VD is just, that means the drain voltage versus ground, which is equal to VDS. So that's also straightforward, right? So VD is VD is simply equals to VDS. All right, which is simply equals to all of this. Let me just copy this again. Okay. So, all right. So what's left? So we got VS. We got a 3 at the back here. We got VDS. All right. We got ID and we got VGS. VGS. Oh, we haven't got VGS. Okay, let's have a look at VGS. All right. So let's have a look at VGS. Now, what is VGS? Well, VGS is okay. So what is VGS? Well, I can write VGS as equal to VG minus VS, right? Well, we know what VG is because VG is just negative VG minus 0. That's what I was trying to write. Okay. So therefore, it's just negative VGG. All right. So VGS is just negative VGG. So just to so that means we've got everything already. So ID is simply this expression here. This is for like I said, an N-channel MOSFET. Sorry, JFET. Okay. So just to give a bit of background in terms of what all these means. So here's the input characteristics of a JFET. Okay. So what we've basically done is we worked out that VGS at the Q point, so VGSQ, that's what that means, right? Is VGS at the Q point is simply negative VGG. That's that part here. And basically, this is the equation. You know, it's the equation of this straight line. It's a vertical line going up. VGS is simply equals to negative VG. So it's a straight line going up. So this is, if you like, the operating line, if you like, of the biasing network. Okay. And the ID curve here is just from this quadratic equation. So wherever the two lines cross, that is our Q point. The point where we've biased the device at a particular point, that's here, so that when signals do come in, it will vary from this point. Just to compare that with what happens on the output side, okay? So imagine that we have a particular Q point, okay? So that means it has a particular VGS value called VGSQ. This is an output characteristics where there is a set of VGS curves, right? So once we set a VGSQ, that means it will set into one of these particular curve. Let's say, for example, this one here. All right, okay, and the VDS will depend on the value of ID that flows, right? Okay, so a small change in ID would result in a big change in VDS. So a big change in VDS. So that's the amplification part. All right. Of course, we need to ensure, of course, we don't go past the breakdown region because we need to work in the saturation region for the device to act as an amplifier. Okay. So I hope that helps. Thanks. See you guys next video.